Hello, welcome to our program, Astronomy for Everyone. Our show this month is about meteorites. In the studio with me are my two guests. To my immediate left, Sandra Masica, and to my far left, Dave Lacko. Now, Sandra, you've done some work with NASA and meteors?
Yes, from about 1996 through 2005 in California, I worked with NASA where we did meteor studies.
And Dave, you have your own meteorite company?
That's correct, Don. I own Dejar Meteorites, participate in local rock and gem shows and astronomy events.
Great. Well, I'm glad to have you both here in the studio with us today. Now, we're going to start out with a very basic question, and that is, where do meteorites come from? Sandra, can you tell our viewers about that?
Sure. If you've ever seen a shooting star, you've seen a meteor. Because shooting stars, they're not stars at all, but they're pieces of debris as small as a grain of sand, or they can be huge boulder type size. And when the Earth is traveling through space, if it meets up with a piece of debris, the debris will hit the atmosphere, and the friction between the piece and the atmosphere will cause the atmosphere to flame up around the piece of debris. So as it's moving through the sky and the atmosphere is burning, it looks like a flaming object or a shooting star. And if it actually lands on the Earth, it's no longer a meteor, but a meteorite. And there's a relationship between comets. Actually, there can be debris for any number of reasons, but we have concentrations of debris in space where comets, as they travel around the sun, comets are basically dirty snowballs with lots of bits of dirt and ice and such. And as they're traveling around the sun, you've seen the tails, it's actually leaving bits of debris in a ring around the sun. Like a ring around your bathtub, only a ring of debris around the sun. And so then as Earth is traveling around the sun, if it intersects that place, that ring of debris around the sun, there'll be a lot more debris there, and so we'll see meteors during that time. And there's several different known meteor showers. One of the biggest is the Perseids, which you see in August, and because the Earth travels around in a uniform way, it meets that same intersection of the debris from a particular comet. And so in the mid-August is the Perseid meteor shower. Another big one is the Draconids, which is in mid-October. Then the Leonids, which is in mid-November, and the Geminids in mid-December. And August is, the Perseids is a good one because it's nice and warm out to be able to go look for meteors. And people often ask, where do you look? And that's an easy answer, you just look up.
Look up.
Right.
Now, I understand that really the best time to view a meteor shower is really after midnight towards morning.
Right, because then the Earth is actually rotating or turning into the space.
Into that debris field that
Right.
we're traveling through in space. Any other ways that we can encounter meteors besides these meteor showers?
There's actually any time that there happens to be a random piece of debris in space. It could come from the asteroid belt or from just any reason at all. You can see meteorites. If you're in good dark skies where there's not too much light pollution, you can see a meteor.
Meteor.
Right.
Yeah.
And then when they land again, that's when they become the meteorite.
Exactly. I think that confuses a lot of people, the difference between the two terms. I'm glad that you were able to clarify that for them.
Okay.
Anything else about the origin of meteors?
Well, there's a couple of different types. Maybe we'll talk about that as we get into the different types of meteorites.
Actually, that's what we're going to move into next. There are basically 4 types of meteorites that can be found. And we're going to learn about those 4 types and also how they're formed. And Dave, what's the first type, the most common?
The most common is your stony meteorites. They account for about 90% of all known meteorites. They're probably the most primitive of them. Your stony meteorites are divided into 2 classes, your chondrites and your achondrites. And the difference between the two is the fact that your chondrites have a small grain or circular grain in there, and that's called a chondrule. And the chondrules were formed, one of the current theories is during the solar nebula, when our sun was just forming, that it was a hot, gassy mixture, and they heated up very quickly, cooled very quickly. And I like using the analogy when you see the astronauts in space take their orange juice and they squirt it to show everyone they're in no gravity. The basic shape is generally a spherical shape or a dog bone shape. And this is a natural tendency to be a circular shape. And your achondrites do not have these chondrules in the mixture, in the matrix.
So that would be the basic difference between
The two in the chondrites.
in the chondrites, which make up the stony
Meteorites, correct.
stony meteorites. Now the next one.
Do we have a picture of one of those? The stony meteorite? This is one example here. And there, I think we have one on the screen now.
There we go.
Right.
Now next up would be the irons. And Sandra, what do we know about iron meteorites?
Yeah, the iron nickel is the second most common of meteorites that we find on Earth, and that's only about 7.5%. The stony meteorites is the most of them.
Far
actually.
away, yes.
And this is an example of a meteorite I have that's a Gibeon meteorite, and it's made of nickel iron and a few some other trace elements. But when you hold these, many people find they seem very heavy because they're made out of nickel iron. And this one has been cut open, and there's a one side that looks sort of burnt and natural, and then there's the straight sides that we see, and you see this almost like a crystal structure or a pattern inside on the surface of the meteorite.
I see we have one
throughout the
had one up there on the screen to
Right.
demonstrate that crystalline structure.
Right, and that is actually almost like a fingerprint that where anytime a meteor falls on the Earth and it has that structure, and the iron, most meteorites don't have that because most of them are the stony type, and it has to be the iron nickel type that has this pattern in it. And all the iron nickel ones don't have this pattern. Some of them do and some don't. And this pattern, actually, these pieces were formed inside like a planet or a moon or some type of a body that had an iron core, a nickel iron core. Like the Earth has an iron core, but it's not cooled down yet. As we have the magma and the heated central
Yes.
portion of the Earth. But something like possibly the Moon and Mars may have done their cooling down completely and have a smaller iron core within them. And if for some reason one of those bodies that had an iron core, a collision or whatever, broke that apart, fell on the Earth, and there's usually, they often break up, so there'll be several pieces, many pieces. And this one from the Gibeons was found in Africa in 1836. It's actually much older than that. It could be into the hundreds of thousands or million years old. And any one that's found from that particular fall will have a pattern just like this, where the angle between the different lines and the width of the lines will be the same. Those are called the Weidenstatten pattern, from the guy who first told about those. And I have two examples here of Gibeon meteorites. One of these was purchased in a rock shop in California, and another in Michigan. But we can tell that these patterns are the same, so we know that they both come from that Gibeon.
We can tell by their fingerprint.
Right, their fingerprint. Which
Exactly.
Exactly.
Now the third type is actually a combination of the first two, Dave?
Yeah, the third type is stony iron, and where that forms is around the core of the parent body, almost like the eggshell around the iron body. And as it cools, one of the first minerals to solidify out of magma is olivine. And you can see the olivine in here. And as the light passes through it, it almost acts like, I like saying it's like the stained glass of meteorites. It's the prettiest of the meteorites, and it's the rarest form. They have, out of all the known meteorites, they account for only about 1.5%.
That's not very many.
No.
So that's the combination of the previous two called stony irons.
Correct. It has the iron matrix with the olivine crystals, which is the stone.
Now the last type is called a Tectite. Sandra, what about those?
Yeah, they're actually not meteorites, but they come from meteorites. And
How so?
When a large meteorite strikes the Earth, maybe the ones we're talking about, like a meteorite that landed and caused the extinction of the dinosaurs, huge meteorite like this. When it lands on the Earth, the impact has so much energy from the speed and the size that it actually melts the dirt of the Earth or the ground and splashes it up into space, where it then gravity will pull it back down and it will cool, and they tend to look like glass because and I think we have an example of this moldavite. This is one of the types of tektites I have here. And they have lots of interesting little bubbles, and you hold them up to the light and you can actually see through that they look like glass because, of course, we make glass from sand or silica. And so they'll have a translucent look like that. And the moldavite is the green type that we just saw, and those are believed to be about 700,000 years old, and you can find those in Czechoslovakia. The other type I have here is an Indochinite, which the one I have here came from Thailand, but they're all about the area of Indonesia.
Okay.
And although this one looks much darker and you don't really see the glass, the example I have here in my hands, it have some little thin parts towards the edge. And again, if I hold this up to a bright light source, I can see that it is in fact translucent.
Well, this is all very interesting, the various types of meteors and meteorites that we have. We're going to take a quick break. If you have any questions about astronomy, please visit our website. You'll be able to see the address there down at the bottom of your screen. And we're going to go next to Term of the Month with Steve Whitty, and right after that we'll be back with more about meteorites.
The term of the month for March 2012 is extrasolar planet. Now, an extrasolar planet is a planet that orbits a star other than the Sun. So this is something outside of our solar system. As of the middle of February 2012, 760 extrasolar planets have been confirmed. Now, they're not very easy to spot, they're not very easy to find, and so you might have a detection of an extrasolar planet, but it really needs some confirmation. You need a lot of data to really prove your case. And the reason why it's not easy to detect an extrasolar planet is that the star is about 1 million or more times as bright as the planet that you're looking for. And so it's a lot like looking for a firefly that happens to be right next to a searchlight. Now, direct imaging has been used to spot stars, spot planets going around other stars, just a few times. Now, this image is from the Hubble Space Telescope, and in 2004, you can see in the inset on the right, there's one image, and in 2006, you can see that the dot has moved, right? So and then the little tiny square, that's the big square that's not blown up. In the center, you have a black spot, and that's the coronagraph on the Hubble Space Telescope. That's basically blotting out the bright central star, but they have put in a dot there that shows where the star is. Now, the very first planets were discovered not around sort of normal stars. They were discovered around a pulsar, and that was done with radio telescopes. So a pulsar is a neutron star, and it has a magnetic field that isn't at its sort of its north pole. It's offset somehow, and because of it, it shoots out a jet of radio waves our way, and as the neutron star rotates, the radio waves sort of come at us in pulses. And the timing of the pulses is very regular, and subtle changes in the timings can betray the existence of planets orbiting the neutron star. In 1995, we had the first confirmed discovery of a planet around a sun-like star, and this is 51 Pegasi, that's the name of the star, and it was found using a technique called radial velocity. It turns out that with spectroscopy, you can tell the radial speed, that is, from our perspective here on Earth, you can tell how fast another star is either moving away from you or coming toward you. And as a planet orbits around a star, the star gets pulled either toward us, toward the planet, or away from us, again by the planet. And so the radial velocity technique, which has been used to find most of the extrasolar planets that have been found, that was used to find a very big star, a very big planet, a Jupiter or bigger sized planet, in a very tight orbit, tighter than Mercury's orbit around our sun. The transit method is the second most prolific of the methods. And basically here what you're looking at is the brightness of the star. And if a planet comes between us and the star, then the star dims just a little bit. There is a satellite, the Kepler satellite, and it has come up with 1,235 candidates by staring at 150,000 stars continuously from space. About half of the sun-like stars that we've looked at have planets. And that suggests that there are 160 billion planets in the Milky Way, in our galaxy alone. Term of the month for March 2012 is Extrasolar Planet.
Welcome back to our show. Now, Dave, suppose I'm walking along somewhere and I see a rock on the ground and I pick it up and I think it's a meteorite. How do I know that it really is a meteorite and just not some regular Earth rock?
You know, that is the most popular question I get asked. And one of the things that draws our attention to the Earth rock, or to a particular rock, I should say, is it's the color, or something didn't look right with that rock. It may have a funny shape, or you picked it up to move it and it seemed heavy, or the color just didn't look right. And one of the things that you can look at on the outside of the rock, a lot happens as this rock or the meteorite came through our atmosphere. The first thing, as Sandra was saying earlier about the meteorites, as it comes through our atmosphere, it starts to heat up. It hits a denser air, and as this denser air and the rock is traveling at such a high velocity, stuff's starting to melt and it's being pushed away or bladed away. And these areas are called thumbprints or regoliths, and we can see them right in this rock here, and it's almost a feel to it. The other thing that happens to the rock as it's coming through, or the stone, is the outside gets burnt, or it has a texture similar to an orange peel skin. It looks smooth, but it has a unique texture to it. The other thing that I tell people to look for is if it is magnetic. About 90% of Earth rocks are magnetic, and what I suggest is that you use a rare earth magnet versus a refrigerator magnet. Because your stone meteorites, since they're the most common, they also have a large variety of metals associated with them. Some have a lot of iron to them, and some have very little. So a refrigerator magnet sometimes won't stick that well, where your rare earth magnets stick very well.
Okay, so that would be one test that a person
That would
could do.
be, well, we've actually went through 3. The touch, the reglaments, or the thumbprints. Is it magnetic? One of the other things is most people, when they see a stone that has holes in it, if it has holes in it, that's most likely not a meteorite, because those are the weakest part of the stone, and as it was coming through our atmosphere, that would have been ablated away and actually turned into a thumbprint and not a hole.
So that piece of slag that somebody finds and they think it's a meteorite,
Exactly.
its very nature would say, no, it's not.
Exactly. I mean, holes in the meteorite, you can almost look at a piece of slag and say, no, that's not a meteorite. One of the other things that I tell people to do after they pass some of the outside tests is to make a little window in the stone to look on the inside to see what the inside is. And what we're looking for, again, are those chondrules, where we want to see, is it iron? Are there the olivine crystals in it? So there's a lot that we can look at inside, but I tell people don't cut the stone in half, because that might damage it if it's a rare meteorite. Just make a little window. It's all we need to see inside.
And this is something that they would have to take it to a rock store or someone as yourself to be able to cut this window.
Putting a window in a meteorite is fairly easy. All they take is some sandpaper and just grind it down to make a little window, just about the size of a dime. It's all you need to look into it.
So you don't need an expensive or fancy grinder, just
Nope.
some sandpaper? Or?
Just some sandpaper and a little bit of time, about 15 minutes to make a window.
Okay.
And with that, as I was saying, some of the reglaments, some stones have a characteristic, because since there's not a lot of temperature, since stone meteorites don't conduct heat very well, your thumbprints are very shallow and very minor, where your iron meteorites can be very dramatic and easy to see.
Because it would conduct heat more and thus
More heat
Get
and be pushed away.
more material being
Ablated.
pushed away.
Yep.
So these are some basic tests that people could do to try to determine if they had a true meteorite. I suppose they could bring it to a natural history museum, perhaps, or some type of a science center. If someone there was an expert at this.
Universities will look at stones a lot. Science centers. You can go to rock shows. There's generally 1 or 2 people at rock shows will be able to tell if it is a meteorite. But most universities or community colleges, the geology departments will look at them.
All right. Well, this gives our viewers an opportunity to validate their stone, to be able to tell. Now, what can we learn from meteorites in terms of the big picture?
What we learn is what happens to our Earth and how our solar system developed. The early ages, the building blocks of our Earth is actually this material.
So this goes back really to, as you say, the beginning of our solar system, as that giant
Yeah.
cloud condensed out and...
Exactly. It's almost like a CIS show dating back billions of years.
a 4.5 billion year old window into the formation of our solar system. That's pretty heady stuff. Pretty heady stuff. This has been great. I've learned an awful lot from the two of you, and Certainly, I'm not an expert on everything in the show, and I certainly wasn't on this, so I was an avid learner of all of the material that the two of you have been able to bring to our audience today. Is there some place where they can go to learn more? Sandra, anything that you can think of that for our viewers?
Of course, there's the internet. You can get a lot from there. I like to look at Wikipedia, and some of the pictures came from there.
Libraries, how about you, Dave?
Or another example would be an astronomy club. You could go to, if there's our Ford Astronomy Club here centered in the Dearborn area in Michigan, and if you join in on an astronomy meeting, you could ask people there.
All right, great. Also, they could see somebody at a rock show too, I'm sure, right, Dave?
Yep, that's a good place to see them.
Well, I hope you've enjoyed our program here on meteorites. If you have any questions about them, or anything else for that matter, you can send us an email. You can see the address there down at the bottom of your screen. And right after our scroll of upcoming astronomy events here in Southeast Michigan, we'll be back with Steve Whitty with What's Up in the Night Sky for March.
What's up in the night sky for March 2012? Before we get to that, on March 10th, the Ford Club is having their annual swap meet. It's a great event. It's something that you really should get to if you can, out on 6 Mile. Look up the Ford Club website for details. Now, the month starts with the first quarter moon, absolutely on the first of the month. That's a Thursday. It's an evening object. A week later, we see the full moon, up all night, on the 8th. A week after that, on Thursday the 15th, is the third quarter moon. This is a morning object. You might see it on your way to work. The new moon is on the 22nd, again, a Thursday. And then the month ends on the 30th with a first quarter moon again. Now, as the month rolls on, most objects rise about 2 hours earlier and set about 2 hours earlier than they did the previous at the beginning of the month. So, and that's for most objects, but there is an exception this month, which I'll get to shortly. Now, the last really easy time to see Mercury happens at the beginning of this month. Just after the sun sets, look to about where the sun actually sets. Mercury is 15 degrees above the horizon. That's about as high as it gets. And it sets about 8 p.m., and it's about as bright as Mars. Now, Uranus is not naked eye visible, but if you have binoculars or a telescope, it's just 4 degrees up and to the left of Mercury. Venus and Jupiter are incredibly bright, and they can't be missed. Jupiter is up and to the left of Venus. Venus sets at 10 p.m. Jupiter sets at 11 p.m. Now, Saturn doesn't rise until 10 p.m. It is a good thing to spot if you can spot it, and the rings are great in a telescope. Now, Mars is on the other side of the sky. At sunrise, at sunset, Mars is in the east, and it travels over to the west during the course of the night. Now, by the end of the month, sunset is at 8 p.m. Venus is above Jupiter and sets later than Jupiter does, breaking the rule that it sets later than it did, that it sets earlier than it did at the beginning of the month. And Venus and Jupiter pass on the 12th at a very close 3 degrees. Mars is still up all night, but it's slightly in a different position. And Saturn rises much earlier at 8 p.m. And that's what's up in the night sky for March 2012.